So here is a question for us to solve, okay? It's a question on radioactivity. It says a small volume of a solution which contains a radioactive isotope of sodium had an activity of 1200 disintegrations per minute when it was first introduced in the bloodstream of the patient. After 30 minutes, the activity of 1 cm³ of the blood was 0.5 disintegrations per minute. Okay, that is missing. I'll add it. 0.5 disintegrations per minute. If the half-life of sodium is 15 minutes, estimate the volume of blood in the patient. Okay guys, I know this is one tricky question you can talk about in radioactivity. I have some ideas I want to use. I don't think that's the only way to go about it, okay? So I'm going to say, if you go through this video and you think the methods I'm going to use were helpful, you can study it and try use it next time when you see something looking like this. Okay, now back to the question. What do we notice first? This sodium isotope had activity of 1200. I can write that dN over dt because it was when it was first introduced into the patient's blood. I'm going to take that as the initial disintegration, and we're told it was 1200. Another thing we are given in the question was the time. After a time, there was another disintegration. That time was 30 minutes. Okay? Another important value given to us is half-life of sodium, 15 minutes. Now, how do we go about this? Now, if I don't want to use this disintegration expression, I can use this as N0, okay? Now, remember there's a relationship in radioactivity that says time of disintegration is equal to number of disintegrations, small n, multiplied by half-life. So I can find out how many disintegrations took place for this to go from 1200 to 0.5 in 1 cm³. So that will give me T over half-life, time of disintegration over half-life of sodium. And time is 30, half-life is 15, number of disintegration is 2. Now, what do I do next? I can say the disintegration after the two moments, okay, is given as N0 over 2 raised to power n. Of course, this 2 means number of disintegration. This is disintegration at the beginning. So we are going to talk about 1200 over 2 raised to power 2. That is 1200 over 4. And that will give you 300 disintegrations. Okay? Now that we have this, we can consider the fact that if 1 cm³ of blood, okay, if 1 cm³ gave 0.5 disintegrations, okay, so what volume of blood will give 300 disintegrations? So when you cross multiply this, you see the volume of blood multiplied multiplied by 0.5 disintegrations is equal to 1 cm cube multiplied by 300 disintegrations. So when you divide both sides by 0.5 disintegrations, I'm shortening the disintegration for the sake of space. This will cancel, and I have that the volume of blood at the initial time is 300 divided by 0.5. That will give us 600 cm cube. Now that's the volume of blood at the initial time when it was first introduced into the blood of the patient. Now, there's another alternative method we can consider. If you think maybe you are having some challenge following this, let's look at this alternative method, okay, and see how easy that can come for you. Okay, now considering the alternative method, you can say the initial volume, let's just say initial volume, call it V subscript 0. Now say, what is initial disintegration? Initial disintegration is given by N naught, which was 1200. Now, initial disintegration per volume is equal to N naught over V naught, which is 1200 over V naught. Okay? Now, after a time t, and whose value is 30 minutes, okay, the volume, call it V1, was 1 cm cube. Then disintegration after this 30 minutes is N over V. That disintegration was given as 0.5. The volume is 1 cm cube. So disintegration after 30 minutes is 0.5 disintegrations per volume. Okay? Now, if this is clear to you, now let's move on. Something else we need to find out. You realize that you can find the decay constant, okay, of this radioactive sodium by using ln 2 over half-life. Of course, ln 2 is a constant value of this. Half-life is 15. So when you divide this with your calculator, 0.693 divided by 15, that will give about 0.0462 per minute. Okay? Having found that, you can use this expression. The activity after 30 minutes per volume is equal to initial activity per initial volume exponential minus lambda t. Now, imagine the volumes were not here. You can erase this, and I'm sure you are aware of this expression. So all we needed to do is, since they were disintegrating per volume, we divide each disintegration by its volume. Of course, N over V, as written there, is N naught over V naught exponential minus lambda t. Of course, this is 0.5, we've written that before, over 1 equal to 1200 over V naught exponential minus, our decay constant is 0.0462 multiplied by time of disintegration, small t, not capital T, of course, is 30. Okay? So here you have 0.5 equal to 1200 over V naught. Now, with your calculator, check exponential minus 0.0462 multiplied by 30. So what you have to do in your calculator is multiply minus 0.0462 times 30. When you get it, check exponential of that value, and when you do that from here, I got the value as 0.25007. Okay, so guys, just simply confirm that to be true. Now, trying to make this volume of blood at the beginning subject of the formula, that means multiply both sides by V naught and divide both sides by 0.5. So you have 1200 multiplied by 0.25007 all over 0.2. Now, multiplying the numerator here, 1200 by 0.25007, that will give you about 300.088, then divided by 0.5. Now, when you divide that from your calculator, you have an approximate value of 600 cm3. So this kind of agrees with the first answer we had using that shorter method. But this one is more descriptive. It's all about you checking it out, and guys, see if you understood any of the methods better and you can use it next time. Thank you.